All right, this is going to be the video for section 4.4 for differential equations. And we're going to learn a method here which will allow us to solve non-homogeneous differential equations where the right-hand side is not zero. There are a number of methods for this, and there are two that are presented in the book that are both equally good, I think, and we're going to pick the one here in 4.4 to cover. There's another one in 4.5 that we're going to skip just because we're a little pressed for time. There's no particular reason why you can choose one or the other. They both do this. I think this one's more straightforward, so we're going to include this one in the class. And this one's called the method of undetermined coefficients. So let's take a look. In order to solve a non-homogeneous differential equation, one that has a right-hand side that's not zero, we're going to take advantage of the superposition principle that says that if you can first solve the corresponding homogeneous differential equation and get what's called the YC, the characteristic, or we'll just call it YC. This is the solution for the corresponding homogeneous equation. So you can think of the C as being for the corresponding equation. And then you can include the right-hand side and find somehow, through maybe like a guess and check method, you can find some solution for the particular equation. Then it turns out that it can be shown that the linear combination of the solution for the corresponding not or homogeneous differential equation plus the one solution that you found for the particular for the differential equation with the right-hand side included, the non-homogeneous equation, when you take a linear combination of those, that solution is the complete general solution. So the general solution is a sum of a solution of the corresponding homogeneous differential equation plus any particular solution of the non-homogeneous differential equation. Okay, so this method of undetermined coefficients we're learning in 4.4 is a good method we can use to find this particular solution. Okay, and what it will result in, well, we can use it. There are some limitations on all of these methods. The limitation on this method is that the right-hand side function can only be a linear. It can have multiple terms, linear combination of terms added or subtracted. The things that are in the terms can either be polynomials or exponentials or sines or cosines. But we can't handle things like 1 over x's like reciprocals or tangents or logs, things like that. So there's a limitation there. This method wouldn't work there, but it would work for really complicated right-hand sides, even like this. Okay. All right, so it's pretty flexible, and it goes like this. Basically, what we're going to do to find the particular solution is we're essentially going to guess what it is, but we're going to use a table to help us with what form we should make the guess, depending on what constant or what terms are included in the right-hand side. So we'll use this table, which you get to use on the test, to be able to guess the form of the particular solution. And these forms have their own associated constants, separate from the C1, C2 constants that are in the general solution for the corresponding equation, right? So we go ahead and assume this is one of these forms. We take the derivatives, plug that into the non-homogeneous equation, differential equation with the right-hand side, and then we solve for these constants. And if we're able to solve for the constants that complete this form, then that means that this form was the right form to choose, and we therefore have our particular solution, okay, for that particular right-hand side. So we could kind of procedurize it like this. First, we're going to find YC, which is the solution of the corresponding homogeneous differential equation. So we're temporarily set the right-hand side to 0 and solve that using any methods that we already know. And then for the particular part, we're going to, well, I'll call it the particular part. We're going to select a form from the table that most closely matches the right-hand side. Okay. Now, if when we do that, we get a term where that term is matching any term in the corresponding solution, then that means that those two would be absorbed and then we wouldn't be getting any additional term to handle the right-hand side. We call that being absorbed, that the term here is being absorbed, and I'll show you this in an example. So if that happens, what we do is we use the term from the table, but we tack on, multiply an extra x to that. Right? And it can actually be an x or an x squared or an x cubed. We take the lowest power of x that we can include, which will make that term no longer match one of the terms from the characteristic solution, from the corresponding solution. Okay, so once we have that yp, then we take the appropriate derivatives and plug that into the differential equation with the right-hand side filled in, and we will get some sort of a system that we can use to solve for the a, b, and so on constants in yp. Once we find those, we plug those into form yp, and then the general solution is the homogeneous solution plus this particular solution. And that solution will still contain the C1 and C2, etc., that came from the solution in step 1. And then there's a 7th step if we have initial values. If we have an initial value, then we can further, now that we have the entire general solution, we can further plug in those values to solve for the remaining constants from the corresponding homogeneous solution. All right, so let's just take some examples. We'll start with this one, which is pretty straightforward. We have a second order differential equation here, right? So the first thing we would do is set this equal to 0 temporarily and solve the homogeneous equation. So let me go ahead and do that. If we have y double prime minus y prime plus 1/4 y, 1/4 y equals 3, or equals 0, sorry, equals 0. This one is linear, right, with constant coefficients. So I could use the auxiliary equation method for solving this. I could say, all right, m squared minus m plus 1/4 equals 0, right, which happens to factor into m minus a half times m minus a half equals 0. And since I have m equals positive 1/2 repeated, that means that my corresponding homogeneous equation solution is going to be some constant times e to the 1/2 x plus c2 times, since we have a repeated root, we have to tack on the extra x, e to the 1/2 x, right? All right, and this will be the sometimes call it the characteristic solution or the corresponding solution. I'll just call it yc. This is yc. Okay, so nothing new so far if that was a homogeneous equation, but now we're going to learn the method for handling this on the right-hand side. So we're going to be working on yp, the particular solution. Kind of confusing terminology, but we'll call it yp, the book does. And so I go looking at this table. This is a polynomial of degree 1, right? 3x plus 1. So if you look at the table, it looks like if I have something of the form, a polynomial for degree 1, then we should guess that yp is ax plus b. So I will start by using the table to postulate a possible form, okay? Now you have to look and see whether any of these terms match forms in the YC solution, and they don't, right? I don't have an x term and I don't have a constant, so I'm good to go here. Nothing is being absorbed. So I'm just going to take the appropriate derivatives to plug this into this equation, which will allow me to solve for these constants, right? So I need a first derivative, so y prime will be a, and I need a second derivative, y double prime will be 0 because a is a constant. So now I'm going to take the differential equation with the right-hand side, which is y double prime minus y prime plus 1/4 y equals 3x plus 1. And then I will substitute all these derivatives in. So I'll put a 0 in for this, right? And then for y prime, I'm going to put a. And then for the y, I'll put the postulated x plus b. Okay. And then I have to find constants a and b in this case that will make this true, right? So if I multiply this out, I have negative a plus 1/4 ax plus 1/4 b equals 3x plus 1. All right. And then that means I have an x term, right? I have a term that's 1/4 a times x. And then I have a term here that's negative a plus 1/4 b that contains no x's. This is the constant term. And this is equal to 3x plus 1. So what we do to find the constants is we match the coefficients. So 1/4 a must equal 3, and this term here has to equal 1. So I'll make a little system there. It's that 1/4 a must equal 3, and negative a plus 1/4 b has to equal 1. That constitutes a system, and we use that to solve. In this case, we could solve for a. We would get that a is 12, right? And then now that I know that's a, I could just plug that in with substitution. Negative 12 plus 1/4 b equals 1. So that would be 1/4 b equals 13. And therefore, b equals 13 times 4, which is 52. So now that I know what a and b are, I can write them in this to get the yp, which is a is 12, x plus 52. And then to form the general solution, y, it's going to be yc plus yp. So the final solution here is c1 e to the 1/2 x plus c2x e to the 1/2 x, and then plus this yp, so plus a 12x, and then plus a 52. Okay, and then, so this is the solution. We still have these constants. If we needed to establish these constants, we would need an initial value. Okay, so that's really how it works. We just solve the corresponding homogeneous equation. We guess a solution for the particular one using a table, and we establish its constants, and we tack that on to the other solution. Okay, not too bad. So there are some complicating things that can happen. One of the things is that you can have terms that get absorbed, and this is a good example to show that. So let's say we have this differential equation, right? Let me go ahead and solve the corresponding homogeneous equation first. Y double prime minus y prime plus 1/4 y equals 0. That happens to be the same equation we just had before, so I won't go through the steps again. It's the same thing as we had over here that led to the solution yc equals c1 e to the 1/2 x plus c2 x e to the 1/2 x, right? So that was the same left-hand side. We're changing the right-hand side. So the yc didn't change from the first problem. But now we're going to postulate a new yp over here. Okay, and this one has two terms. And we're going to have to use the table for each one of them. So let's first look at the constant term. Right, the constant term, it says if you have one or any constant, then the particular solution will be, the yp will be just a constant a. Okay, so if I were to replace for this one, I'm going to include an a, right? And then for e to the 1/2 x, let's look through here. We have e to a power of x. So this is just going to be a constant times e to the power of x, right? So I've already used the a constant, so I'll use b, but it's the same exponential with a constant attached, right? So we'll call the next constant b. So we're going to add b times that same exponential, e to the 1/2 x. Okay, and then normally I would take my derivatives and substitute, but here's the problem, right? Right now, this term's okay, the a, because there's no constant term in the yc solution, but I already have a constant times 1/2 x term here, right? Which means this term right here would be absorbed. I wouldn't actually get another term on here for yp because whatever happened would just be absorbed in here, right? So I'm not able to do that. So here's how we handle that. We just go ahead and multiply this by an extra x. So this will be bx e to the 1/2 x. But unfortunately, that also would be absorbed. So since this would also be absorbed, we're going to go up to bx squared e to the 1/2 x. You just keep tacking on another x until you get something that no longer matches. So that means this is going to be my yp, a, some constant plus some other constant times x squared e to the 1/2 x. All right, so now I need to take my derivatives here. I need a first derivative and a second derivative. So y prime will be, that's a constant, so it's 0. I've got b. Now, you know what? I'm going to have to do a product rule here. So I'm going to lump the b in here. So it's going to be first times derivative of the second plus second times derivative of the first, which would be 2bx, right? All right. And then when I do the second derivative to plug in here, I'm going to have to take both of these terms and have product rule because they both have the variable in them. So I've got first times the derivative of the second here, which will be another 1/2, so 1/4 e to the 1/2 x plus second times derivative of the first, 2bx. And then I have to do the product rule for these terms. So I have first times derivative of the second, which would be 2b, right? Plus second times the derivative of the first. So 2bx times the derivative of the first is 1/2 e to the 1/2 x. Okay. So yeah, let's see if we can combine some terms here. Maybe we can make this a little easier to deal with. Well, you know what? It's all going to come out in the wash anyway. So let me just now plug these three things in to the differential equation with the right-hand side established. So first I need y prime. So I have another copy of this. I've got y double prime. So 1/4 b, this first term, x squared e to the 1/2 x. Okay. And then I've got a 1/2 and a 2, which cancels. So I have a plus b x e to the 1/2 x. Okay. Then I've got a term here, 2b. This is a b here. Okay. So 2b e to the 1/2 x. Okay. Then I've got the 2 and the 1/2 cancel. So I've got a b x e to the 1/2 x. Okay. There's y double prime. And then I have to subtract y prime, and y prime is this. So I'll subtract. So minus b. Let me go back there because it's minus 1/2 b x squared e to the 1/2 x. Okay, and then minus this term also. So minus 2b x e to the 1/2 x. Okay, there's the minus y prime. And then we have to go plus 1/4 y. So it's going to be plus 1/4 of each of these terms. So plus a fourth a plus a fourth b x squared e to the 1/2 x. And that has to equal 3 plus e to the 1/2 x, right? So we've written this equation out again, but filled in all the derivatives. All right, so let's take all the terms. First of all, we've got some x squared e to the 1/2 x terms. That's this one and this one, and this one. So we've got, let's see, a fourth and a fourth is a half. Minus a half means these cancel. These all cancel to 0. Okay, and then I've got an x e to the 1/2 x term, right? So that's this one, and this one. And it looks like I've got, let's see, is that right? X e to the 1/2. So 1, 2, minus 2. Those are also canceling. Good. Okay, and then I've got this, which is an e to the 1/2 x term. And that's the only one. So let me write that. We've got 2b times e to the 1/2 x. And then the other term over here is this, plus 1/4 a. And that has to equal 3 plus e to the 1/2 x, which means that 2b has to equal 1. So I can start making a system here. 2b has to equal 1, and 1/4 a has to equal the constant term 3. All right, so it looks like we've got b is equal to 1/2, and we've got a is equal to 12, right? And so that means that my particular solution, yp, is a, right, which is 12, plus, let's see, it's going to be b, which is 1/2, and then we ended up with this one. These ones got absorbed, so we had to use x squared e to the 1/2 x. So x squared e to the 1/2 x. And that means that our general solution now is c plus. So the general solution is yc plus yp. So we're going to have the c terms, c1 e to the 1/2 x plus c2 x e to the 1/2 x plus 12 plus 1/2 x squared e to the 1/2 x. So there is our full solution. And there's still two constants left, but we can't establish those unless we have an initial condition. Okay, so that's how that would look. And let's just go ahead and take a look at what it would look like if we had an initial condition. So if I'm given an initial condition, the next one in the notes is this exact same problem, but we now have an initial condition. So we go through the part of solving YC and then guessing YP and finding the constants and finding the general solution here. What if then we are given an initial condition? Well, that therefore means we can find a constant from this, right? If I take when x is 0, y is equal to 14, let's change colors here, then that means that, well, I'll go ahead and use red for the original equation, right? If I plug in 0 for x, the y has to be 14. So if I plug in 14 over here, then I'm going to get constant 1 e to the 0 plus constant 2, 0, e to the 0, plus 12 plus 1/2, 0 squared, e to the 0. Right, so these e to the zeros become 1, but this has a 0 in it, so this goes away and this goes away. So this just ends up being c1 times 1 plus 12. And so if this is true, then if you subtract this over to the other side, it turns out that c1 has to equal 2. Okay, and then we could take the derivative of this to use this initial value. So to take the derivative of our solution here, y prime will equal 1/2 c1 e to the 1/2 x, right? And then this term here, we have to do product rules. So we're going to do the first times the derivative of the second plus the second times the derivative of the first. Then we have a constant here, so its derivative is 0. And then again, I have a product rule here. So let me group the 1/2 in here. It's going to be first times derivative of the second plus second times derivative of the first, which would just be x. Okay, so now that we have that, we can plug in 0 for x, and y prime must be 4. So this 4 happens when we have x is 0. So that would be e to the 0 plus c2 times 0 times 1/2 times e to the 0 plus e to the 0 times c2 plus 1/2 times 0 squared 1/2 e to the 0 plus e to the 0 times 0. So anything with a 0 here goes away. But that means that 4 equals 1/2 times c to the 1 times 1 plus e to the 0 is 1 times c2. But I know that c2 is 2, so this is 1/2 c1 plus 2, which means that 2 has to equal 1/2 c1, so c1 has to equal 4. Is that right? Getting a different answer than I got on my formula sheet here. 1/2 c2 equals 4. Oh, I plugged it in wrong. Yep. Sorry. Let me back up. So at this stage, I have 4 equals 1/2 c1, right, times 1 plus 1 times c2. This c2 actually goes in for this one. So we have 4 1/2 times 2 plus c2, which is 4 equals 1 plus c2. So c2 has to equal 3. And that means then that we can write our general solution as now a full particular solution. Let me switch colors here. So this is going to be the general solution is now we can fill in c1 and c2. So c1 turned out to be 2, so it's 2 e to the 1/2 x. c2 turned out to be 3, so plus 3x e to the 1/2 x plus a 12 plus a 1/2 x squared e to the 12x. And there's our final particular solution. Okay. All right. Okay, let's take a look at one more example, and this one is a general solution. So let's do that to wrap this up. This is a triple or a third order differential equation has a third derivative in it. So y triple prime minus 6y double prime equals the right hand side. So first, we'll go ahead and find the corresponding equation, which is homogeneous, which is y triple prime minus 6y double prime equals 0. This one is a linear differential equation with constant coefficients. So again, I can solve this with my auxiliary equation. It would be m cubed minus 6m squared equals 0, which means you can factor an m squared out, which means we have m equals 0 with multiplicity of 2, and we have m equals positive 6 with multiplicity of 1, which means that I'm going to have for my YC solution, it's going to be some constant times e to the 2x, right? I'm sorry, 0x. It's going to be some constant times e to the 0x, plus, because there's a second multiplicity, c2 times x e to the 0x, right? Plus this term here, c3, which will be e to the 6x, right? But e to the 0x is 1, so really this is saying we have some constant plus c2 times x plus c3 times e to the 6x. Okay, so there is my general solution, or my YC for the corresponding equation, the homogeneous equation. Okay, now we'll guess a form for YP from the table. Okay, for the constant, we're going to put in a. And then for cosine, if we look at the table, I can, for either cosine or sine, you put a cosine and a sine term of the same argument, but with separate constants here. Okay, so it doesn't matter that this is a minus. I'm just going to go ahead and add generically because this constants could be negative. I'm going to put a constant times the cosine of x plus a different constant times sine of x. So we need a cosine and a sine term to replace a cosine, according to the table. Now, are any of these absorbed? Well, this constant here is absorbed because I have a constant. So I'm going to have to replace this one with ax. But I also have a constant times x. So I'm actually going to have to go with ax squared for this one so that this doesn't get absorbed by either this term or this term. Okay. There is no cosine here, though, or sine, so we can use the b cosine x and the c sine x as is. So here's our postulated guessed particular solution. So we'll have to take triple derivatives of this. So let's take the first derivative first. This is going to be 2ax, and then the derivative of cosine is sine, so negative b sine x, and then plus c cosine x. Y double prime, the derivative here would be 2a. The derivative here would be minus b cosine x, and then minus c sine x, right? And then y triple prime would be, that's a constant now, so that's 0. So this would just be now positive b sine x, right? Because derivative of cosine is negative sine, and then minus c cosine x, right? All right. So now we're going to plug this all into this non-homogeneous differential equation. We have y triple prime, which is, let me do it down here actually. So we've got b sine x minus c cosine x, c cosine x minus c cosine x. You know what? Yeah, c cosine x. Okay. And then minus 6 times this. So I'll take negative 6 times each of these. So negative 6 times 2 is negative 12a, positive 6b cosine x, positive 6c sine x. And then that's it. There's no use of this derivative or this y. That's equal to 3 minus cosine x. All right. So let's see, we have a constant term, right, which is negative. So we have negative 12a, right? That's this. And then I have a sine term here. So I have b plus 6c sine x. And then I have a negative c plus 6b cosine x term. And that has to equal 3 minus cosine x. So there's a 1 here. Right. All right. So the constant negative 12a has to equal 3. B plus 6c has to equal 0 because there's no sine term over here. This is confusing the way I wrote that. And then we have to have the cosine coefficient negative c plus 6b has to equal -1. There's the system. So it looks like a can be computed by itself. A is -3/12, which is -1/4, right? And then b and c will have to solve simultaneously. So you know what? Let's just negate. Well, if I write these in order, we have b plus 6c equals 0, and then 6b minus c equals -1. If I multiply this equation by 6, I would have b plus 6c equals 0, 36b, right? 36b minus 6c equals -6. So I would have 37b equaling -6. So b would be -6/37, right? All right. And then that means that C would be, let's go to this one. If I solve this, it's going to be C is equal to 6b plus 1, right? So if I take 6 times b, which I now know is -6/37 plus 1, that's going to be -36/37 plus 1, which is 37/37. And so that's going to end up being 1/37. Okay, so now that I have the constants, I can make the solution. All right, so the solution, the general solution, is going to be c1 plus c2x plus c3e to the 6x. And then we're going to have these terms up here. So I ended up with a constant a, which is -1/4, -1/4. And then I have a b constant, so plus b cosine. So the b was negative, so it's going to be -6/37 times cosine x. And then I have plus c times sine, and c turned out to be +1/37. So 1/37 sine x. This is the general solution. All right. Okay, so that is it for examples here. Hopefully that's enough to get you off and running so you can try the homework on section 4.4.